Students, this is the Electron Arrangement in Atoms lab. And in this lab, your classmates in class will be receiving laminated cards with two sides to them. And on those cards, they're going to place little pencil erasers to represent electrons. And then on the other side of the card, which you'll see a picture of later in the second half of this video, they'll use markers to write electron configurations and also place pencil erasers to show the arrangement of electrons in atoms. What we're going to do is a screencast with a picture of each side of that laminated card and work through the same problems. The only difference is instead of using pencil erasers to make electrons, we'll make marks on the picture. So you will need a periodic table to complete this. And whereas your classmates are, and actually you can do this too, you can take screenshots of the various electron arrangements and upload them into the lab report. It's just that we'll have markings on a picture rather than pencil erasers. Okay, so let's start with the front side of the card that is pictured here. And it is called front side of the card Bohr model picture. So we're going to think of the Bohr model diagram. And according to this model, electrons orbit the nucleus the same way that planets orbit the sun. Notice that in the center of the picture, there's a red sphere labeled nucleus. The first ring around that is the first principal energy level, n equals 1. And in that first ring or principal energy level, there's one box representing the one orbital that you find in that first principal energy level. The second ring around the nucleus, n equals 2, or second principal energy level, has 1, 2, 3, 4 boxes representing the 4 orbitals that you find in the second principal energy level. Of those 4 boxes in the second ring, notice that one of them is a little bit darker than the other. And if you look at the key to the lower left, it says the dark box represents the s orbital. The slightly lighter colored box represents one of the p orbitals. And then as we get further along and further away from the nucleus, you'll see d and f orbitals. Like in the third ring around the nucleus, there's one s orbital. There's 1, 2, 3 p orbitals, along with 1, 2, 3, 4, 5 d orbitals, representing the appropriate number of orbitals that you'd see there. Okay, we're going to mainly focus on the inner 3 rings. In fact, I don't even know that we'll get to the, oh yeah, we will. I think we'll get to the third ring. But we're mainly going to keep our eyes on those innermost rings. Let's start with a Bohr model picture of helium. So helium, if it's neutral, and we should presume neutrality throughout this exercise, it would have 2 electrons to counteract the 2 protons that you'd find in the nucleus. Always starting from the innermost ring and building outwards, then we should see 2 electrons. I'm just going to use circles to represent those. So here, the 2 electrons fit into the orbital of the 1s sublevel, as shown here. Go ahead and snap a picture or screenshot this. And then I'm going to clear the frame. And we'll move on to oxygen. Oxygen has atomic number 8, so 8 protons, which means that if it's neutral, we should see 8 electrons as well. Elex. Okay, so starting with the innermost ring, we'd fit 2 electrons. The second ring, we'll start with the s sublevel. Could fit 2 more. So thus far, we've placed 4 of the 8 total electrons. Now for the 2 p orbitals, Notice that I'm going to place one electron in each box until I have to double up, until we're forced to. So thus far, just placing one electron in each of the three p orbitals, that gives us 7, but we need to get to 8 in order to represent neutrality. So this is what neutral oxygen's Bohr model would look like. Go ahead and snap a screenshot. I'll go ahead and clear the frame. Now for phosphorus, element 15, symbol is P, so we've got 15 protons, and if it's neutral, then 15 electrons. Again, starting from the innermost ring, you can place 2 electrons, another 2 in the S sublevel of the second ring, and this one's going to take a few circles here. Notice the order in which I'm filling these is I put 1 electron into each p orbital until I have to double up. At this point, we've placed 10 electrons, but we're not done yet. Going on to the S sublevel of the 3s sublevel, we've got 2 electrons in the 3s sublevel, and that brings us to 12 total electrons. But we still need to get to 15. And in order to get to 15, I'm going to put 1 electron into each of the p sublevels, or into each of the p orbitals of the 3p sublevel. Go ahead and take a screenshot of this one. Okay, now I'm going to clear the frame. Next element, sodium, Na. That's element number 11. So we should see 11 protons and 11 electrons if it's neutral. And once again, we're going to follow that same order. Start with the innermost sublevel, and then as you move outwards, fill the 2s sublevel, then the 3p sublevel. Again, it's 1 electron each until you have to double up. And in this case, we're going to fill the second principal energy level and get just 1 more. If you look and count up the number of circles, we've got 11 total. And that last electron should go into 3s sublevel. Go ahead and take a picture. And we'll clear the frame. And then it says in the lab report, draw a Bohr model picture of an element of your choice. Ooh. You could have picked numerous, there are numerous options here. An element of choice. How about we go to sulfur? I'm just picking one for fun here. So sulfur has 16 protons. It's element number 16. If it's neutral, it'll have 16 electrons. So starting from the innermost ring, that's 2, and then 2 more in the 2s sublevel. We're going to end up filling the second principal energy level here. So far, we've placed 10 electrons, so we got to keep going. Here's numbers 11 and 12. And then for the 3p sublevel, I'm going to put 1 electron per box until we have to double up. And we do have to double up here. So we've placed 15 so far. And that's electron number 16. Go ahead and take a picture. And we'll clear the frame. Now we'll move on to the backside of the Bohr model, backside of the laminated card. And I'm going to pause this video and restart. Okay, now we've got the backside of the electron arrangement in Adam's lab, the laminated card that your classmates will be working with. And let's take a look at this card. It might look a little complicated at first. This box in the lower right corner that's kind of shaded gray, that's a place for us to draw orbital diagrams and the electron configuration, both the long notation and the noble gas shortcut. So we're going to be writing in this box. The rest of the space along the left edge and at the top of the card is a place for your classmates to put pencil erasers showing the placement of electrons. Now we're going to use markings on this picture instead of the pencil erasers, but the concept is the same. And if you look closely, the dark boxes are the S sublevels. The slightly lighter shaded boxes are P sublevels. The even lighter shaded boxes are the D sublevels. And then way up high, which we won't get to because you don't often see these, the dashed boxes are the F sublevels. Notice that they range from, they are written in vertical order of the order in which they're filled. So the very first sublevel to fill is the 1s sublevel, followed by the 2s, and then just above it, but to the right, is the 2p sublevel. Just above that is the 3s sublevel, and just above that is the 3p sublevel. Notice that it gets really, really close right about here between the 4s and the 3d sublevel. They're super close in energy, but the 4s is slightly lower, so we fill it first, then the 3d sublevel, and so on. We won't have to worry about sublevels beyond those I just mentioned because we just don't deal typically with super big atoms. Okay, looking at the lab report, it asks us to draw the electron configuration and orbital diagram of boron first. So boron is an element with symbol B, and its atomic number is 5. So that means if it's neutral, it's going to have 5 protons and 5 electrons. Okay, so if I were to place the pencil erasers, I'd go in order here, putting 2 in the 1s sublevel, followed by 2 in the 2s sublevel, followed by just 1 electron in the 2p sublevel. In terms of electron configuration, we'll simply write those numbers. How many circles did we put in the box of each sublevel? 1s we put 2, 2s 2, 2p 1. And then you don't have to write anything else. In terms of a noble gas shortcut, well, okay, helium would take the place of the 1s2 portion of that electron configuration. So it doesn't really save you a ton of writing, but that's because it's a small atom. We'll see later that really does, the noble gas shortcut does save you a lot of writing. So our shortcut would be helium in brackets 2s2, 2p1. Now for the orbital diagram, this is where we draw arrows pointing in opposite directions, indicating a knowledge of opposite electron spin. I'll put 2 arrows in the 1s blank, 2 arrows in the 2s blank, and then just 1 arrow, it could be pointing up or down, it doesn't matter, in the first blank of the 2p sublevel. Go ahead and take a screenshot of this. That would be our electron configuration and orbital diagram of boron. Okay, now I'm going to clear the frame. The next element they ask us to draw is magnesium. Magnesium is element number 12. So that means it necessarily has 12 protons. And if it's neutral, it also has 12 electrons. Starting at the bottom and working our way up, 2 electrons in the 1s sublevel, followed by 2 in the 2s sublevel, followed by 6 in the 2p sublevel. Notice that I'm filling these 1 circle per box until we have to double up. At this point, we've found a home for 10. We've got to get to 12 because there's 12 electrons for magnesium. So I would stop here. And then just noting what we've written so far, 2 circles in the 1s box, 2 circles in the 2s box, 6 in the 2p box, and 2 in the 3s box. We can shorten that a little bit by writing neon in brackets. That takes us all the way up through 2p6. So I'm just going to rewrite what comes after 2p6, and that is 3s2. So this time we actually did save some writing, neon and then 3s2. Orbital diagrams, this is the one where you put arrows on the blanks. The arrows should be pointing in opposite directions. We had put 6 electrons in the 2p sublevel. Sorry if my drawing isn't great. And then we ended with the 3s sublevel. And I would stop there because that's 12 arrows. Go ahead and take a screenshot. And I'll clear the frame. Next one is silicon. Silicon is element with the symbol Si, and it is element number 14. So 14 protons, and if it's neutral, 14 electrons. Starting at the bottom along the left side, we'll place 2 electrons in the 1s sublevel, 2 in the 2s, and I'm working my way through the 2p sublevel. Notice that you can, each little dot in the box shows you where you can put a circle. Sometimes my drawing isn't awesome, but we're trying. And then I'm counting circles. Thus far, I've drawn 15. So my next circle is going to be in one of the boxes of the 3p sublevel. It doesn't matter which one, but I got to put it somewhere. And that takes us to, oh, wait a second. Oh, one more. Let's see, 13, 12. 1, 2, 3, 4. Oh, okay, I went further than I needed to here. Sorry. Let's take that back just a step. Sorry. Now I'm counting carefully. There are 14 circles, only 2 of which appear in the 3p sublevel. Okay, now let's correct that. Electron configuration-wise, how many circles did you place in each sublevel? 2 in the 1s, 2 in the 2s, 6 in the 2p sublevel, 2 in the 3s sublevel, and 2 in the 3p sublevel. The previous noble gas was neon, and neon's configuration, as represented in brackets there, takes you all the way up through the 2p6 sublevel. So what follows after element 10, neon, is 3s2, 3p2. And if we make an orbital diagram, we'd follow that same pattern, but instead of using circles to represent electrons, we're using arrows in the boxes. Make sure that the arrows within each box are pointing, blanks, are pointing in opposite directions. And then for the last sublevel, the 3p sublevel, the 2 arrows should be on opposite blanks, or different blanks rather. There's a third blank that doesn't have anything in it, but the other 2 blanks each have 1 electron. Go ahead and take a screenshot. Okay, I'm going to clear the frame. The last one, argon. Here's element number 18. So we should have 18 protons for argon and 18 electrons. So if we follow in order here, we'll place our electrons on the boxes. I'm not so good at drawing, but we're going to work on it. Thus far, we've placed 10 electrons. We got to get to 18. And as it turns out, notice that argon, which is a noble gas, has a completely filled third principal, or at least a 3p sublevel, which means it has extra stability because its boxes are completely filled. That's what makes it non-reactive. So our electron configuration goes 1s2, 2s2, 2p6, 3s2, 3p6. Now you might say, for the noble gas shortcut, can I just put argon in brackets? Technically, no. You have to go to the previous noble gas. So you have to go to neon and then write what comes after neon's configuration, which would be 3s2, 3p6. Now for the arrows in the boxes, we're simply putting the same number of arrows as we've placed circles in the boxes on the left side. And then apologize for the sloppiness here. Each arrow within a box points the opposite direction. If you count them up, we should have 18 total. Go ahead and take a screenshot. I'll clear the frame. And the last one, it says, pick an element of your choice. I like fluorine, so I'm going to say, let's draw fluorine with 9 protons, and if it's neutral, 9 electrons. And within the 2p sublevel, we're going to be almost filled, but there's a blank space right here. So that leaves us with a configuration of 1s2, 2s2, 2p5. The previous noble gas is helium, not neon. And thus, we're not saving a ton of writing here with the noble gas shortcut. It goes helium in brackets, 2s2, 2p5. In terms of arrows, we should see 2 arrows in the 1s box, 2 arrows in the 2s box, and then a total of 5 arrows in the 2p box. Go ahead and take a screenshot. And that's it for this lab. Thank you very much for your good work.